go back over to here. So I guess I can come here and I can just we'll start new. All right, so let's start. Let's just see how fast we. I mean, okay, that maybe sounds bad. Let's see how fast we can solve this. All right, but yeah, kind of. Draw a box, and now what I want to do is cut out some interior piece. I build a wrench box. And you see how it says R1 plus polynomial 1 up there, R1 plus P1? I'm putting a minus sign in there. I want my domain to be R1 minus P1. Go to boundary mode. Okay, there I have it. Okay, right now, what I've got is two boundaries, and my domain is that box minus this. So what we could clearly study right now, study its state flow of a wrench. Okay? All right. Or, you know, actually when you design a wrench, this is actually nice. Finite element, in fact, they do this for tools, right? You want to say, where's the stress points? How do I design a better, Craftsman wrench or something like that? Suppose you work for Craftsman or NASCAR, and you're trying to design a better wrench for Jimmy Johnson. All right. So what would you do? Well, you would make this complicated geometry, and you'd say, I know all this. I know the relationships of stress tensors. And I just put those equations in under complicated geometry, and then I'd say, I got some tough guy pulling down here, and I got a nut right in there, and say, where are the stresses? Complicated geometry, complicated things acting on it, and I can apply forces the right way, and I could, in fact, model the whole stress on this thing and say, look, I need reinforcement here, there, not much. What? I mean, you could just do all this, right? Okay, that's how you do this. Now, see, you can build your own power tool company right now after this class. Okay. So there we go. For the moment, let's make some cooler boundary conditions, like so some dude's pushing on this down, and I'm gonna. Where did the screen go? There it is. Okay. Oh, there's my rotation. Whoa. Sweet. It was hiding the whole time. It wasn't that it was hiding. I see you. Let's rotate that by 10 degrees. Oh, Bandhu. What happened? Come on, man. You're killing me. We're just having fun. I have no idea what just happened. I love being able to say, I'm not an expert. I have no idea what happened there. All right. Okay. So let's go back and draw a wrench. I'm going to. That's an angry bird. All right. And we're going to make our domain, the area around it. Okay. And I say, boom. Oh, no. Go back here. There. Okay. All right. Somehow I didn't pick that up. All right. There we go. And let's say over here I'm going to enforce some kind of boundary condition. I don't know. Right now it's Dirichlet, but let's force some kind of Neumann instead. Some flux condition across there. Let's make G like 20 and Q like cosine X. Whatever we want to do. Okay. And over here let's pose some condition as well. Neumann, let's say, I'm just making stuff up, by the way, right? So presumably, when you come to this code, you wouldn't be making stuff up. You'd be for real. Okay, whatever that means. All right, okay. Great. See, I got this domain. I got these boundaries. I put them in there so something cool might happen. I can specify a PDE. And let's just do, sure, the same PDE. How's that? That's okay with everybody? Okay. And then you just say, triangularize that. Boom. Probably a little more resolution. Look at that. Jiggle it. Nice. Okay? They should just call that the Fresh Prince button. I think I'm going to write them a memo. If you want a cooler product, call it the Fresh Prince button. Trademark. All right. There we go. And we're going to solve this PDE on that mesh, and you just say equals. There is the solution. Hey, where's my other plotting box? Oh, here we go. There we go. All right. So I've got contours. So here's the solution so far. Look at that. What's going on? This giant angry bird's going to sucked up in that vortex. All right. Maybe we don't need to see 3D, so let's take that off. Plot. Okay. Huh. I did something. I screwed something up. Are there pictures below it? Oh, it's right there. Okay. It actually has my solution there. Okay. There it is. So there's my solution. And again, you can start doing whatever you want. You can take off your mesh. You can put in, you can instead put in a XY grid. So so now these aren't the points. These are just a, oh, I lied. I don't know. It doesn't show an XY grid. Actually, it does somehow. You can't see it on the screen there? No, you can't. Okay, never mind. Let's forget I just said that. Let's just do that. Arrows. That tells you a little bit about the direction of the flow. See here, see the arrows big in there? That's that vortex of death that this bird is flying towards. Okay? So anyway, there you go. See how simple it is to use in some ways? Okay? So this is kind of where we're going to end this example. My hope is that what we're going to do Friday is we're going to come back and now go back to that airfoil problem and try to set that up for what we want to do. Okay, we'll rewrite it down, put it in, try to do some kind of airfoil calculation off that. Okay? But it's quite remarkable that with very little, ultimately the whole purpose of all these boxes is to do what? Hide you from having to allow you to focus in on things you presumably would like to focus in on, which is getting an answer to a problem. Now, there are people who are interested in the whole, like, I want to build up some really hard math to do it. Okay, and that's a valid thing to do, and there are people who do that. That's why you go to math grad school. Okay? But if you want to take this and actually use it, right, then you want to be able to just say, look at this. All I got to do is either import or draw my domain, specify the boundaries. You are kind of limited, right? You can't have a nonlinear boundary condition. You have to have things that fit under those buttons. Same thing with the PDE. Here's your biggest limitation, those two buttons right there. Specifying the PDE, specifying the boundary. But domain triangularization, trivial. Give it any geometry, it'll do it. The equal sign just goes and solves in what these are. Okay? So that's the main thing. And any of these commercial packages, that's pretty much what they do. They walk you through. I believe many of the PD toolboxes that you would get basically, and by the way, you can also make it vector quantities instead of just a scalar. But many of the toolboxes you might get will often have example files for your field of application. Suppose you're doing heat transfer problems. You go to the examples, heat transfer. And it's almost all set up for heat transfer. Like, oh, if you're doing a heat transfer problem, this is the kind of problem you're solving, and here are the typical boundary conditions. All you got to do is specify those. You're doing computational electrodynamics? Oh, well, you need to specify these things. It's already set up. So it's almost like it's taken all the work, even ahead of time, out for you for that specific problem. set it up completely for you, right? Fantastic, because then you can just do amazingly complicated geometries with like almost no work. You just put it in, and you just love it. Just hit the equal button. It does all the work for you. Okay? So that's the basic idea. We'll come back, try to calculate lift off the airfoils, and finish.